So now this is the next and the last very important point of this chapter, which is about maximum and minimum values of a function. This is sometimes also called maxima or minima. Maxima or minima, that means maximum or minimum values of a function. So what we'll do here, let me just write here, we with the help of derivatives, that is using derivatives, of course this is a part of applications of derivative. Using derivatives we get the maximum or minimum values of different functions, various functions. This is what we want to do. We'll discuss what we mean by maximum and minimum values of a function. Now here what we do, basically we find the points in the maximum minimum. We find points at which graph of function reaches its highest or lowest locally. I'll discuss what we mean by locally. We find points at which graph of function attains or reaches its highest or lowest locally. Okay, and these points are called here local maximum, where the function attains highest is called the local maximum value, and when the function attains minimum value, that is at lowest, that's known as the local minimum value. So I'll just draw a graph here. You will realize what I'm trying to tell you. Suppose I'll consider one rough graph over here for some function over here. This is x-axis, this is y-axis, this is just origin over here. Okay, now suppose I'll consider such graph like this here. It starts at A, it ends over B here. Suppose I have a graph like this, for example. Let's take like this. Okay, define on the closed interval AB. Now you see here in this portion function increases, so its derivative will be positive. Here function decreases, so its derivative will be negative. This is one turning point where the function attains the highest value. This is known as which point? Turning point here. But this is not the highest in the entire domain. In small portion it attains the highest value. So if I call the C1 here, then at C1 function has the highest value. So we call this as local maximum value. Where? At C1. And how do you find the local maximum value? By finding f of C1. So over here function has a local maximum value. Now come to this here. This is the lowest value in this small region. So if I call this as, for example, C2, then over here the function has local. Why we use the word local? Because it is not the lowest in the entire graph. It's the lowest in this small portion. So we have local minimum value over here. At C2 function has a local minimum, and local minimum you can find by putting x equals to C2 in the graph of the function. So over here f of C2, it will come from the y-axis. Same way, what about this? If I call this as C3, for example, here C3 over here. So this is again local maximum value in the small region, it may not be highest in the entire domain. So we use the word here locally or the local. What about this? As you know, here also function has a, if I call this a C4, then here also function has a local minimum value. This is the lowest point in the graph. This is the highest point. In the sense of locally means what? Not in the entire graph. In small portion it attains the maximum. In small portion it attains the maximum. Here it attains the minimum. Here it attains the minimum. Okay. So we call sometimes these points as a turning points, right? So local maximum or minimum points where the function attains the local maximum minimum values are called turning points. Are called, what we call them, turning points. Turning points. There the function takes the turn. These are called what? Turning points. Turning points means what? There the function changes direction. You can see in the graph. These are known as turning points. You see here it was up, now it is down. Down, it goes up. So function has changed the direction. Down goes up. Function has changed the direction. Going up, down. Function has changed the direction. Going down, coming up. Function has changed the direction. So these points are known as turning points, where the function has a local maximum or minimum values. Fine. Again, I'm emphasizing local means what? This may not be highest in the entire graph. It may be, but not in general always. See, this is not the highest value in the entire graph, but in the small region of C1, in the small region this is highest. This may not be lowest, this may not be the smallest value, but in the small region here it is the smallest value. Fine. That's one thing. I hope this is clear to you. Local maximum values or local minimum values, these are called what? Here maxima or minimum, right? We'll do all these things with the help of derivatives because this is a part of application of derivative. Now here, in this function, in this portion, function increases. So if you remember earlier section, its derivative is positive, right? In this portion, function decreases. So its derivative is negative. Here positive, here negative. That means at this place the derivative of the function must be 0. Fine. So whenever there is a turning point, its derivative at that place must be 0. F dash x must be 0. Right? So whenever f dash x is 0, that means the function is turning from there. So whenever f dash x is 0, then you can see that here function has a local maximum. Now come to this, here it was decreasing, so f dash x is negative. In this portion it is increasing, so f dash x is positive. That means here again the derivative must be 0. That means whenever from this you can conclude if function has a local minimum or local maximum, then its derivative must be 0. Here 0, here 0. Fine. Again over here positive, its derivative here negative, so at this place the derivative must be 0. Here f dash must be 0, here f dash must be 0, here f dash must be 0. So what we conclude from this graph, it's quite obvious also because positive negative, so here it must be 0. So whether the function attains local maximum value or local minimum values, derivative must be 0. That's the first important conclusion here. Fine? Clear? I hope up to this you are fine. If function, I repeat, function has a local maximum value or minimum value, then at that place the first order derivative must be 0. It's quite obvious from this. Positive, negative, so here it has to be 0. Positive, negative, positive, so it has to be 0. Positive, negative, so it has to be 0. Negative, positive, so it has to be 0. So at all these turning points, its derivative must be, first order derivative must be 0. This is, function attains highest, here function attains lowest. I'm emphasizing on the word locally. Then we come to the one more word which is called the globally. Globally means what? In the entire domain. In the whole domain where the function has the highest value. that is known as a global maximum, or sometimes it's called the absolute value, maximum or minimum absolute values. So I'll write that first before I get into the results connected to this. We also find in fact absolute, let me write here, absolute, or sometimes this global word is also used, global, or sometimes greatest word is also used, absolute or global maximum value. And similarly we have absolute, or you can write here global minimum values of a function. Now local and global. Global means what? In the entire domain you are going to find the maximum value. You just look at this graph, you know fx equals to x squared, if you remember this graph. Okay, it's a parabola symmetric about which axis? Y axis. You know it looks like this. Okay, now this is a turning point. This is decreases, so here derivative has to be less than 0. In this portion derivative has to be greater than 0. So here derivative must be 0. Where? At origin. In fact here f dash 0 is 0. So this is a turning point. So as per our terminology, this is local minimum. Not only that, this is the lowest value attained by the function. You know here fx equals to x squared is always greater than or equal to 0. Right? So not only local minimum, so here you can say that the function has absolute or global minimum value at 0. Global minimum value at 0, over here 0. And what's that minimum value? Put x equals to 0 in the function, and absolute minimum value equals to f of 0, which is 0. That you can find by putting x equals to 0 in the graph of the function, so it will be 0. That also you noticed here. Absolute minimum value of the function is attained at 0, and that value is also 0. Fine. It has no largest value, it has no absolute maximum value, because this graph never ends, you know. It has no absolute maximum value because this graph never ends, right? It goes so on. So it has no absolute maximum value. So this become local as well as global. In the entire domain, this is the lowest value. Fine. So now you are clear. Local means what? Not the entire domain. In a small portion, it should be highest. Then it's called the local maximum. In small portion, it is the lowest. Then it's called the local minimum. Fine. And global means what? What do you understand by the global or absolute? That means in the entire domain, it must have maximum or minimum value. So absolute means, so absolute maximum or minimum value means it must have maximum or minimum value in the entire domain, in the domain. Fine, that's what we understand by absolute. And when we use the word absolute or global, that means in the entire domain it must have the maximum or minimum value of a function. Clear? Absolute or global or the largest. Sometimes this largest word is also used here. Largest, global or the largest here. Largest. And here sometimes absolute, or here you can write the global or the least value of the function. Sometimes here largest or the least value of the function. Okay. So here is a theorem based about this local maxima or minima. So let's start with a function here. Let f be a function defined on some interval I, defined on I is an interval. Okay. Now it says that if f has a local maxima means what? Now you know, a local maximum value or a local minima. Minima means what? Local minima means what? Local minimum value at x equals to c, then this is a conclusion, then either f dash c must be 0 as I explained. At that point derivative must be 0, or the second conclusion, if f is not differentiable at that point. Not differentiable at c. Not differentiable means, do you remember? It must have corner at that place. Graph of modulus function. At 0 function is not differentiable in modulus function, if you remember. But it can have a local maxima or minima. Right? So this is very important theorem. What it says, if function has a local maxima, that means local minimum value, or a local minima, that means local minimum value at c, then at that place its derivative must be 0. That we have discussed, right? In the first graph you see here, this is local maximum value, so over here its derivative is 0. Why derivative is 0? You know, here positive, here negative, so it has to be 0 here. Here negative, here positive, so it has to be 0 here. You know very well that now. So either this or it may not be differentiable at that place. Okay. And here points where this derivative is 0 or not differentiable are called critical points. Are called critical points here. Are called critical points. Which points? Critical points. There's such points where this or this are called critical points. So you know, one more time, if I draw for you like this here, if I have function like this, suppose it starts from here like this, now it has a corner here, then it like this, then you see these all are the critical values. So if I call this as C1, here it has a local maxima, so this is critical point. Here it has a local minimum value over here, and local minimum value is this is local minima, this is local maxima, this is local minima, this is local maxima. I'll call that as C3. Now these you cannot find by differentiation, you have corner here, function is not differentiable. Still this is a local minimum value, you can see. Function is not differentiable. If you have a corner, if you remember differentiation chapter, then over here function is not differentiable. So these points are known as critical points, right? So we say here at C1, C2, C3 and C4, you can write at these points over here, these are the points where the function has local maxima. Maxima means what? Again I emphasize, maxima means local maxima means local maximum value, or local minima. Local minima means what? Local minimum value of a function, right? And this local maxima or minima are this local maximum value, or you can write here maxima, and I'll write the local minimum value, that I'll write the minima, where the function has a local maximum value. You can see one is at C1, it has a maximum, and that is given by f of c1. Okay, then f of c3. Fine. At c2 it has a local minimum, so f of c2, that's a local minimum value, and here f of c4. Got it? Understood. You must understand the points where the function has a local maxima or minima, and the local maximum value or local minimum value which are given by this. It comes from the y-axis, you know. At c1 it has a local maximum, right? But what is that local maximum value? That comes from the graph of the function, that is f of c1. At c2 it has a local minimum value, but what is that minimum value? It comes from the graph of the function f of c2. At c3 it has a local maximum, but what is that maximum value? It comes from the graph of the function, which is f of c3, and so on, right? And here these points where the function has a local maximum or minimum are sometimes called here extreme points. Extreme points. Which points? Extreme points. There are a number of new terminology today. Extreme points, and these are called extreme values. Extreme values of a function, of course. Extreme values of f. Extreme values means it combines both the words, maxima as well as minima. These are called extreme values of a function. It means both maxima as well as minima. These are called extreme values of f. Extreme points means what? Either it has maximum value at that place or minimum value. This is common terminology. Get the extreme points. That means you get all the points where the function has either local maximum or local minimum. And extreme values of the function, once you get this, then put these points in the function. So you'll get the values of the function, which may be local maximum or minimum. These are called extreme values of a function, right? Extreme is a common word that includes maximum as well as minimum. Here also it includes, you know, points where the function has a maximum or minimum. Fine? Okay, so that's one thing. This is about turning points. You know, these extreme points are nothing but what? In the other language, turning points. This is a turning point, this is a turning point, this is turning point. In general, these are also called the critical points, right? So critical points, extreme points, turning points, these are the new words for you now. Turning points. All are same, remember. Turning points. Turning points where the function changes direction. So either it will have local maximum or local minimum. Turning points, extreme points, or critical points. But critical points includes points where the function is not even differentiable. Okay, so this is about specially turning points, which is mixed. Now when we say turning points, that means at that place function may have local maximum or local minimum. Now we want to distinguish these two. Out of these two, which one have local maximum, local minimum? So for that, we have one more theorem. We'll just state it without proof. So next we have important theorem, which is called the second derivative test here. So we start with a function. Let f be a function differentiable twice. So you can find double derivative at c on interval I. So I is an interval. Then here the first part is if its first order derivative is c is 0, second order derivative f double dash at c is negative, then the conclusion is, this is very important conclusion, then the conclusion is here x equals to c, that is point c is a point of local maxima, point of local maxima. What's the meaning of this? That means at this place the function has a local maximum value. This is 0 and this is negative. Double derivative is negative. That's why this is called the second derivative test. That means f of c becomes local maximum value. Local maximum value. And where that local maximum value you will find at c. That's why it's called a point of local maxima. At c, function has a local maximum value, and that local maximum value is given by this f of c, as I explained. So this talks about c1 here. At c1, function attained highest in the small portion. It attains the highest or reaches at highest. But what is that highest value? That is this f of c1 here. Local maxima or local maximum value is f of c1. But this is the point where the function has the highest value. Okay. Without proof we are stating. The second one is if f dash c is 0. It has to be 0 for turning point. And double derivative now we are saying that it is greater than 0. There it was less than 0. Then in this case x equals to c, that is this point c is a point of now a local there it was the local maxima, here it is a local minima. Is a point of local minima. There it was local maxima. And therefore what is f of c? F of c is nothing but local minimum value of the function of f. Of course, here also I should write of f function, right? So the second condition talks about this c2. At c2, function has a minimum value. And what is that minimum value? That is f of c2. It comes from the graph of the function. So that's what I have written. And now third important condition, that is if we have this, if f dash c is 0 and its double derivative is also 0, both derivatives are 0, then this test fails. Then test fails. Test fails. Right? Then you need to see actually from the behavior of the function and so on. Then with first order derivative, that is f dash x with first order derivative, we'll see examples. You'll realize with the first order derivative we need to find at c f has local maxima or minima or not. It's quite possible function may not have local maximum or minimum, right? And such point is called point of inflection. I'll write that the point where function has no local maxima or minima is called the point of inflection. Let me write as a remark here. If f dash x is 0, then usually we consider that the function must have local maximum or minimum. But sometimes even if f dash x is 0, but I'll show you by graph, you'll realize, but function has no local maxima, that is no maximum value, local maximum value, or local minima, that is no local minimum value, then such a point is called point of inflation. So this is one more new word, point of inflation. That means their function has uh, no maximum value or no minimum value, but still the first order derivative is 0. Right? Normally what we have in our mind, if first order derivative is 0, then the first function must have either local maximum value or local minimum. That is local maxima or minima. But sometimes it's quite possible that even the first order derivative is 0, still function has no local maxima or local minima. Such a point is known as a point of inflation. Look at this graph here. If you just recall, it's not difficult to draw. Fx equals to x cube, cubic function. You know its derivative, that is fx equals to 3x squared, double derivative, you know 6x. Fine. Now it's a cubic function. If you just recall, you can draw the graph very easily, but just for your information, I'll show the graph. The graph is like this here roughly. This is the graph. It's like this. This is a graph of fx equals to x cube. Now over here at 0, if I take x equals to 0, so c becomes 0 here. You see f dash 0 is 0. Here f double dash 0 is also 0. Here both the derivatives are 0. So here you cannot consider above theorem. That means we cannot use the above theorem. Because here you see this is not the turning point. Even at that place the first derivative is 0. This is not the turning point. Still the function has fx. Function is fx equals to x cube. Has no local maxima or minima at x equals to 0. So here this point x equals to 0 is called which point, as I explained? Point of inflation. Point of inflation. It's called the point of inflation, where the function has no maximum as well as no minimum value. You can see here first order derivative is 0, but still here graph goes up. So f dash x is positive, increasing. Here also increasing. Here also f dash x is positive. You can see. So here graph goes up only. Function increases every time, even it passes through origin. Normally in the first graph, if you recall, when f dash x is negative, then in the other part f dash x was positive, and vice versa. As we were discussed in the first graph, you look at this. Here positive, negative. So this is turning point. This is called the critical point. This is critical point. This is critical point. This is critical point. Positive, negative, negative. Here f dash x is going up, so positive. Here f dash x is positive. You see graph goes up. Here f dash x is positive, but still the first order derivative turns out to be 0. So function has no maximum as well as no minimum value at 0, and such a point is known as what? Point of inflection. So point of inflection and critical points are different. Don't get confused with this. Now let's note two important things. The first one, if a function is defined on, say, real number r, that is on infinite domain, like such functions fx equals to x squared, fx equals to, let's say, modulus x, such functions, then we may not get maximum value. Maximum means what? Absolute maximum. Or minimum. May not get the absolute maximum or minimum value of f. Like you consider this parabola, okay? So here minimum value, minimum value equals to 0 at x equals to 0, but no maximum. Graph goes up, but it has no maximum value in the sense of absolute maximum, remember. Okay, if you consider even like this, let's consider such graph. For example, like this, you can think of how drawn the graph of which function. Now you see at 0, this is the highest value, right? This is a graph of which function? Can you think? Minus of modulus x. Fine. So this is the highest value. So here function has, you can write absolute or just maximum. Absolute maximum at 0. At 0 it has the highest. Absolute maximum at 0. And what's that absolute maximum value? Which is also 0, because f of 0 is 0. But here f has no minimum value, right? Graph goes down and down, right? It has no minimum value. So this happens if the function is defined on infinite domain like R. Even you see the one more graph as we were discussed in the earlier slide before few minutes. Look at this graph. Okay, see, so it goes down and down like this, it goes up and up like this. So here you know fx equals to x cube. This function has neither maximum, this function has neither maximum, absolute maximum, nor minimum value, nor absolute minimum value, right? So these are the several possibilities if the function is defined on R. It's quite possible it has minimum but no maximum. It has a maximum value but no minimum value. Here it has neither maximum nor minimum, right? It depends upon the function. If the function is defined on the infinite domain, especially like this on the real numbers. Okay, so that is the one thing I wanted to emphasize. Now second thing, we may have function on the closed interval. Second part, that is function is defined on closed interval. Function is defined on closed interval. Defined on closed interval, say a b. Okay, so like this. Suppose here this is a, this is b. Suppose function is like this. Okay. Now, can you see graphically where the function attains the lowest value in the entire domain? Over here you see, this is the lowest value at A. Where the function attained the highest value? At B. Is it? So absolute here, absolute maximum, that is the global maximum, is at B. At B it attains the highest in the entire domain. This is local maximum, local minimum, local maximum, local minimum. But what's a global or absolute maximum? At B, and f of B is absolute, or you can just write maximum value of f. Fine. Okay. What about absolute minimum? Absolute minimum from the graph is at A. And f of a, that is this one, f of a is minimum value, absolute minimum value. So in other language, minima of f. Fine. All these are the points, turning points, where the function has local maximum, local minimum. This you can find from the derivatives. If I draw the graph like this, then this is one example here. If I draw the graph like this, then suppose I have function like this on closed interval, of course, like over here, then it goes up, here down, it goes up, and then over here. Okay, like this. Okay, local maximum, local minimum, local maximum, these are the values at two endpoints. Fine. Can you see in the graph where the function has the highest value? If I call this as C1, if I call this as C2, if I call this as C3, then at C3, which was local maxima, and now it become the global maximum value also, right? So at C3, f has, you can write absolute maximum. Got it? It is of course a local maximum because it is a turning point, but it is the highest in this domain. Starting from this to this is the highest point where the function attains the value. And where is the lowest? Over here. So at C2, f has absolute minimum. There it was two endpoints, right? What I'm trying to tell you here, both minima and maxima were at endpoints. Here it is somewhere at the local values. You see, this is local minima, but now it becomes the global also. F has absolute minimum. This was of course a local, but now it becomes a global also. Clear? So whenever the function is defined on the interval, what we'll do? Every time we are not going to draw the graph in the function. So to find, we'll use this whenever the function is defined on the interval to find the absolute maximum value. What we do? We take the maximum of what? All the points where the function attains the local maximum, like here, this. So maximum of local maximum value. And what else? Can you say this? See, in this graph, if I take the, suppose this is 20 and this is 25, then what's the maximum? That's a 25. So that becomes the absolute maximum value. But if the graph is like this, then if I take these two only, suppose here it is 10 and here it is 11. If I take 11, will it be highest? No, you need to consider endpoints also. So here, what you need to add? F of A and F of B. Understood? Have you realized why I've added these two? If I take just maximum of these two, see, these are the two maximum, local maximum values, these and this. If I take the maximum of these two, shall I get the absolute maximum value of the function? No, because here absolute value, maximum value is at B also. So I need to take the f of B also. Sometimes it is quite possible that a graph is like this. So I need to take f of A also. So absolute maximum value, when the function is defined on the closed interval, you take all local maximum values and two endpoints. And the same way here, absolute minimum value equals to, now we are going to take what? Minimum of, that's the smallest, minimum of all local minimum values, here local maximum values, all local maximum values. Now you look at here, see, there is only one local minimum value, that is this one. So maximum will be itself, and that will be the absolute minimum value. Fine. But you look at this here, these and this. If I take the minimum of these two, will it be the absolute minimum value? No, because minimum value is attained here. So I need to add two endpoints also, f of A, f of B. Right? So we use these to get the absolute maximum and minimum value of a function using this concept. Maximum of all local maximum values and f of A and f of B. All local maximum gives you all these pick points. You take the maximum of these and this. You will get the absolute maximum. And absolute minimum means what? You take the minimum of all local minima. That is these and this. 1, 2, 3 and 4. If you take the minimum of these 4, you will get the absolute minimum value of a function. If the function is defined on the closed interval. If it is defined on R, it depends upon the function. Fine. So this is all in all about theory related to 6.5. Now we'll go to 6.5. Very, very important exercise.